Hi everybody, my name is Shiza, and in this research paper video, I'll be analyzing detection and grading of gliomas using a novel two-phase machine learning method based on MRI images. And so the reason why I decided to analyze this research paper today is because, as I mentioned in my previous video, I've been looking into doing the BRATS challenge. And so for the BRATS challenge, the thing is, the images, we already have access to them, my team and I who's working on this. We have access to them, but we don't have that much insight into the image because we have the MRI scan, but we don't know about the annotations, the ID. We know that they're like a certain type of tumor, but we don't know the grade of the tumors, how severe it is. And all of that stuff is beneficial, as it says in the research paper, for something called prognosis, which is trying to find, well, how fast will the tumor grow? Is it likely to spread? All of these insights we can get from just knowing the grading of all of that. But the Brad's challenge, like the data set doesn't have that. And although it was supposed to be available according to the organizers on May 2nd, it hasn't been released yet. And so my team and I have been looking into different methods, and this was one of the main methods that we looked at. Although there was stuff like correspondence and other techniques like that, this was one of the really intriguing ones, at least that I found, and I decided that I wanted to share in this video. So let's start off then, shall we? Okay, so as I said, having the early detection and the grading of the gliomas, that's very beneficial in gaining insight about the brain tumor. And so over the last decade, we've had many advancements in the computer vision industry, but in this research paper, we're not going to be optimizing. We're actually going to be just having this new novel-based approach that combines different algorithms and techniques to form a very accurate method that can detect and grade gliomas. So they're using gradient features, and gradient features are essentially the directional changes in the intensity of the colors in an image. So let's say, for example, you have an MRI scan, one part of it might be a bit lighter than the other part of it. And so that also gives insight into it because you can tell where the edges are, where the corners are, stuff like that. And we'll go a bit deeper into this as well. Like we're looking at gradient features, we're looking at the changes in intensity, and all of that. If we capitalize on that, then we can use this two-phase classification network. So in the first phase, what they're doing is they're okay, so in the first phase, they're looking at the probability of each local feature. So they're splitting up the MRI scan into a certain amount of cells. So it could be like 9 cells as it shows over here. So here we have 9 cells, for example. So they're splitting up the MRI scan into a certain amount of cells. So that's what they're doing first. And so they're looking at each of them, and they're looking at an HOG, which is the histogram of oriented gradients. And obviously, I'll talk a bit more about this because this is just the abstract. So they're using that and they're trying to find the insight in that. So they're like, okay, well, is this disease? Is this malignant? Is this benign? And this is what it's saying. So if it's malignant or benign or malignant for grading, or if it's diseased or healthy for detection, depending on what their task is. And you could do either of them with this novel two-phase classification network. So that's what I'm saying. For each cell, that's what they're doing. And so from there, they're taking the high-level features from that entire whole MRI scan and they're putting it all together. So the thing about this to note, and obviously I'll touch a bit more about this, is when you're performing the HOG, which is the histogram of oriented gradients, usually what happens is like the typical thing is to find the gradients for all of that and then combine it together. But what they're doing here, and this is what it makes it really unconventional compared to the status quo, is that they have the gradients, but they're actually looking at the gradients first and analyzing each cell in the algorithm, and then they're combining all of that. So there's like that one step that really optimizes the process. And so from there, that's basically the first step of it. Now, in the second phase, then they're using a classification algorithm that was obviously like used to train a classifier based on high level features and patient labels. So, just trying to get more insight into stuff like that. I mean, obviously, we'll talk about the framework in more depth. Again, this is just the abstract. Now, the thing is, this is a bit more on the medical side, which I don't focus too much on, but obviously it's still good to know because the thing is with biomedical imaging, you're making some sort of impact. And if you want to make an impact in the healthcare space, at least, you should know how it works. And so there's glial cells in the central nervous system, right? Now, these cells, depending on their features, like they can have different grades. So if you have like a glioma, they can be from grade 1 to 4. So 1, 2, 3, 4. And it depends. So according to the World Health Organization, I believe, yes, who they said that grade 2 and grade 3 are grouped under the lower grade glioma. So because they share like some sort of mutations, some sort of similarities, then they're grouped together in the sense that they're not that severe. However, if you then look at um, grade 4, they're classifying it as a glioblastoma because it has a very high malignant degree and a bad prognosis, as in like the chance of like recovering and yeah, recovering basically. So obviously, since it's because of the lower prognosis, LGG tumors, low-grade gliomas, they have more optimistic outcomes and longer survival times. And they're talking a bit about like the status quo of how they treat the what was it again? The glioblastoma, like surgical resection, followed by radiotherapy, stuff like that. They're just talking more about that. But the thing is, what we want to focus on is the fact that with medical imaging technology, again, we've seen so many advancements in not just the technology itself, but the techniques that are used to find those gradient features. So, you know how I said we wanted to look at the intensity? There's these certain features used in MRI scans, such as FLAIR, such as T1 weighted sequence, all of that's trying to help, um, trying to make the accuracy higher for like looking at the gradient features and capitalizing on those. So that's just really helping with that. Now, obviously, there's, as I said, many advancements, but the detection and the grade identification right now, they're dependent on the visual examination by experts. And obviously, if you're doing this process manually, especially if it's 3D, then obviously it's time consuming, it's prone to errors, it's not efficient at all, things like that. So that's why what they're doing is they're looking at recent advancements. So they obviously, like there's the convolutional neural networks that are being used, and there's a lot of advancements, right, with deep learning, with transfer learning, all of that using different sort of algorithms. But the thing is, the process of distinguishing the tumor boundaries between like the malignant or benign tumor and then the healthy cells, all of that, that's like a very challenging task, like the boundary, because obviously like the contrast between them is not very high. So it's hard to tell where exactly it is. And again, just adding on to the where the problem is. Now, as it says here, we've looked into this. Although deep learning methods have shown excellent performance in the biomedical imaging domain, the thing is their lack of interpretability still is an issue, right? Especially in terms of like the clinical setting. And so what that means is that there's some sort of lack of consistency in predicting a model's predictions. So if you're looking at, for example, a prediction of the model, and then you're looking at what you predicted as, let's say you're an expert, there is a very high difference between that. And obviously, because of the fact that this task is complicated, that makes sense. But if we're using this for clinical practice, then obviously it's not feasible. And so this is what they're doing. Again, they're proposing a two-phase classification framework to distinguish patient from healthy controls or discriminate between, the grades. So this again is see, I keep forgetting the name, but it is, let's see, where is it gone? So lower grade glioma was LGG, glioblastoma. There we go. Hopefully I'll remember that next time. But this is what it's doing. So we have 3D MRI images, right? And they don't have the segmentation of the brain tumor. What we're doing is we're looking at the slices of them. So you have like thin slices of those scans, and that's actually going to be helpful in the future as well, when we're looking at um, when they're analyzing each feature independently and they're looking at the location of that certain cell throughout all these slices, like that's going to be helpful in like trying to find out the grade. So that's like the reason they probably sliced it, plus like it's a lot more accurate to do that. So again, what they're doing is, first of all, in the first phase, they're looking at each cell, right? So they have a certain amount of cells, and they're extracting the local features slice by slice using the histogram of oriented gradients, or the HOG algorithm. And so this is what the HOG algorithm is over here. So this algorithm, what it's doing is it's trying to distribute the directions of the gradients that are used in the features. Obviously, like you can see, there's some sort of arrows, and we'll look into how this works. So first of all, what you need to know is that like gradients of an image, the reason why they're helpful is because the magnitude of the gradients are so large around the edges and corners. So here, I don't know if, yeah, it probably might not be able to show this here, but if you're, yeah, okay, so if you see here, right, the magnitude over here, like look at the size of the arrows, like it's much larger than like these small arrows over here. So if you can tell that the magnitude of the gradients is very big, you know that there's some sort of edge or some sort of corner here because of the larger and abrupt intensity change in the gradient features. Now, if again, if you have something that doesn't change a lot, then you know that it's more of like just within the pixels. They're not edges, they're not corners. And so if you have the gradient magnitude of each pixel as we have here, so this is for 1 pixel, and then along with that, we also have the direction of the high magnitude over here. So this is the direction that it's facing. Then obviously you can get more insight from this as well. Because again, HOG is the distribution of the directions of the gradients that are used in these features. And so it starts talking about that and how it works. And I'm pretty sure we go more in depth into that as well in the next section. So let's move on. So um, okay, another thing that they talked about was the fact that the reason why HOG is also helpful is because it can help when it's trying to differentiate between, the LGG and the glioblastoma, because of the fact that it can tell within the boundaries. And as we mentioned, there's a big problem with consistency and trying to find where the boundaries are, because that is, as it says here, it depends on visual examination by experts, not AI models, but experts done manually. So this is talking more about the materials and the methods and how they got the data. But honestly, I don't want to focus too much on this because the data is obviously such a big part, but the part of this research paper that makes it very unique is the fact that it has like a very unconventional and novel method that in a classification network. So I want to really dive into that. So I'm going to skip a bit over the data acquisition right now, and the image pre-processing. Also, that like I don't want to go too deep into it, but one thing that I really found interesting was that they converted the original DCOM scans to a single nifty image file. And I was like, well, why are they doing that? Because DCOM files are also used for MRI scans. So the thing is, for nifty files, like the data, it's more compact and it's easier to manipulate. Now, over here in the DICOM scans, you have the format of like raw data that's collected by a scanner. So in this case, it would be the MRI scanner. Now, to change it, what they're doing is that you have all of this, right? And then they have like slices of all of this raw data, and you're basically stacking it together, and it would have some sort of volume, right? So it would have like it would concatenate into a time series. I'm not sure if I don't think I have a picture of this here, but I did search it up on the internet, and it made a lot of sense to understand why it's like that. Why is it some sort of time series that shows if you change up the format? So, I mean, I just found that really interesting because usually like people use decom files, but then just converting into Nifty, I was like, well, why are you doing all that for nothing? But clearly it's not for nothing because again, it's easier to manipulate, it's a lot more beneficial, it can also give better accuracy. So things like that, concatenating to a time series, those benefits obviously outweigh the benefits of the DICOM scans in this case, especially. So that's why they're doing that. They also talked about normalization methods such as bias correction and the Z-score stuff. So I didn't look too much into that, but obviously, like if I were to do this project, I would have to look more into how these normalization methods work. So yeah, I didn't look too much into that. Um, Feature extraction. So yes, they talk about feature extraction here. And this is okay, this is essentially how the HOG, the histogram of oriented gradients, this is how it works. And I'll show you the figures here because that's what it's referring to. Figure 1.A. There we go. Here, these are the cells. So the thing is, the whole MRI image, so it's split up into a dense grid of uniform space regions, right? So you can see that over here, there's 9 cells that we're looking at. And the cell in HOGs, they can be any shape, right? They can be circles, they can be rectangles. But in this case, and obviously this makes sense because you want to preserve the spatial information, you have rectangles because, again, if there were circles, like you'd obviously be missing out. But since the MRI scan itself is literally a rectangle, then obviously, it would be a lot more beneficial if the dense grid of uniform space regions, the HOG, the cells, they would all be in the form of a rectangle instead of circular shape. And again, they also did say that it was also because of better performance, which again, that makes sense because of preserving the spatial information. So I already talked a bit about this, but just to recap, we have the magnitude, and the magnitude is basically saying the arrow length, and then the arrow direction is the gradient direction that it's talking about here. And so which channel is selected, that basically depends on the calculated pixel gradient direction. And what I mean by that is if you go back to the research paper, this is what it talks about. So here it's let's see, how's it called? This is called orientation binning because it's used to generate the cell histogram. And you have you have 8 channels or bins that are evenly distributed in like a 360, like a circle basically. And so depending on where you see most of the arrows pointing, so here you can see most of the arrows are pointing like this way, a bit like this way, mostly to that side, obviously. So we're going to be putting most of the shaded area over here, and then that's basically what it's showing here. And then because of the frequency, you can see that from here to here, like it's basically just showing the change. It's basically showing the frequency of the like the weighted number of pixels that are distributed in different direction channels. Yep, so it goes deep into that, and then we start talking about the two-phase classification framework. So obviously, I mentioned that we're using HOG. So in HOG, we're usually using it for things like pedestrian direct detection, stuff like that, because I mean, boundaries and stuff. I mean, segmentation could always do that, but this is also a very good method to do that because you can tell like if they're walking in a certain direction, like the edges are going that way, right? So it's like you can tell based on that. Obviously, again, segmentation also works. Um, so this is what it says. So since the pre-processed MRI image, which they converted from a DCOM now to a 3D Nifty format, they need to take the HOG features from every single slice because you want to try to get the most accurate information. You can't just use the top layer. You have to slice them up, and then you have to extract the HOG feature from every single slice and then every single cell within that too, in the algorithm. So that's what you're doing, and then and then is that what it says here? And then we concatenate all the HOG features to form a representation of the whole 3D image. Hmm. So that is the status quo. And that's a problem right there that they're talking about. That's a status quo because they're basically saying you take all the features, you just add them together. Now, what they're doing, and I talked about this already, is that they're having those HOG features, then they're analyzing and interpreting and the results between that, and then they're concatenating all this information and like concatenating all this information to get insight within that specifically to get a compact representation of the whole MRI image. And so that reduces the dimensionality of the feature space while also alleviating the overfitting problem. And that there's so many methods to like mitigate overfitting, and I guess this is one of them as well. And then what it's trying to say is that the whole MRI image was sliced into a series of 2D images. And then for each slice, this is like a recap basically. So we're taking out the slices from the 3D image. Then for each slice, we're using the HOG algorithm for each of the cells in each of those slices. And then from there, we're analyzing each feature within that in each cell independently, And then we're looking at like how it can be related to different types, like different cells around it and stuff like that, just so they can get a sense of the boundaries with the histogram of oriented gradients. And then they're also relating it again not only to the things that are surrounding it, but since it's like a stack, right? Since it's a stack of 2D slices, if you're looking at like let's say this cell right here, this cell over here, and the slice of the 3D nifty image underneath, like this would obviously be correlated to the image underneath that is looking at the same cell. So because of that, we're we can extract it from the same location of different brains. And so moving on, then we're looking at this, and this is like a very good representation of how all of this works, how we are looking at every single cell from cell 1 to cell n, and in this case, they have divided up into 9, and then they found the histogram of oriented gradients for every single thing over here, that they split it up into, all these gradients that they have for every single cell for the features. And then from there, they have some sort of classification that is showing, well, now what do you think? Do you think it's disease? Do you think it's not disease? Do you think it's malignant? Do you think it's benign? Depending on if you want to do detection or grading on any of them. So that's what it's trying to say. This is basically the model, and then obviously we're going to talk about the second phase classification as well. They're also talking about the clustering method that's used to determine the classification of n subjects into k discrete classes. Um, so they're looking at two things. So first of all, either there's two types of clustering. K means clustering. There's two types. There's hard clustering, which basically is you have one single cluster, or you have like one fixed point at the cluster, so you can't have like one point that's in between both the clusters. It's with that one specific point. And so soft clustering is basically the opposite because it's flexible and it's allowing each subject to be assigned to more than one cluster. So because of that, then we're like making it more adaptable, and we would also be adapting the number of centroids based on that, because again, if you really wanted to just be constant at one centroid, then obviously like you would need to make sure that the feature is strong enough, and like you would have some sort of sense of clarity of which centroid you want to go to, because again, if it's hard clustering, then it has to be there for sure. Now, they also use like a variation of this k-means algorithm called the fuzzy c-means algorithm, and I don't know where they get these names from, but essentially they're using soft clustering in this, and I would say that's also a very good decision. But they're assigning each subject that's going to be assigned some sort of centroid a probability from 0 to 100% that it falls within that category within that centroid. And so the reason why they're using it is because, again, we mentioned this, is that the boundary between the different types of image features is actually very hard. So you can't just be like, okay, it will go here for sure, right? So because some cells, for example, they might be in both the malignant and the benign brain regions. So that's the thing, like tumors can be half malignant, half benign, like there could be a partial thing. And so that's the main problem, right? Like you want to identify between the boundaries that are usually ambiguous, where the benign and the malignant brain regions are. And so again, if we used the hard thresholding clustering method over here, and we wouldn't consider the ambiguity of all this, then obviously the accuracy wouldn't be that good at all anyways. And so they found that for k-means clustering, they wanted to have two clusters, k is equal to 2. Did go too much depth into this. And then it started talking about how for every single subject they concatenated the fuzzy labels of each feature from the first cell over here, like let's say, and then they move on to the last cell, and then they concatenate all of that information, right? um and since they like already um here, let's see, one second, instead of directly concatenating, right, so they use a clustering method to transform each hog feature to another high level feature, and then from there, like again, we're basically doing that same thing of like having the data dimensionality reduce, and then having the alleviation of overfitting. Basically that's what it's trying to say by using that method where they're doing the hog first on each feature, and then they're finding the high level stuff of that, and then they're combining it, that's saving a lot more computations. So that's what it talks about. And then it starts talking about how a support vector machine would play into this as well, and how it separates the data samples into two classes. Now, I'm gonna be completely honest, this part, it was a bit hard for me to understand because I'm trying to understand how a support vector machine plays into classification. And I know, like, I looked a bit deeper into this, it started talking about this kernel trick, but I think I just have to look more into this as well. And just based on this research paper, I'd have to do a lot more research because the classifications of all the all the individual features, they were all combined over here, as it shows, or maybe it was down here. Here, yeah. So they're all combined over here, the classifications, into a support vector machine. And then it's trained on the second phase classification. It's trained here to then predict the final result of the test brain sample. So for example, does the brain contain gliomas, or what grade the glioma is as well. And so to evaluate the performance of this, what they did is they used tenfold cross validation. And um, I could show a bit more about the website and how it really works, but it's actually quite straightforward. We're validating a couple of times based on different data sets. We're like shuffling it, and then we're like sampling and splitting it up depending on like what the task is, and then from there we're validating it to see how it does on that particular data set. And then since you have a tenfold cross validation, the cross validation would tell you like, okay, is the accuracy like actually for real, or is it not for real? um and then because of the fact that you're doing like tenfold, as you're doing more and more runs with this talks about in the results, as you're doing more and more runs with this, the variance of the model will obviously decrease, because now you're like, okay, well, if you have run it 10 times, then the first one wouldn't compare as much as to the third one. But if you're doing it like 2 runs, then obviously like the variance would be quite big. And so they evaluated the performance of this model with a couple of things. They did it with accuracy, they did it with sensitivity, and they did it with specificity, and they did it with area under curve. I've never heard of, I mean, I've heard of area under curve, but the mathematical explanation behind it also doesn't make complete sense to me, to be completely honest. But other than that, like accuracy, we know could be using different things like dice loss, stuff like that. Sensitivity is basically the total, the total, yeah, the true positives. 1 second, let me quickly check this. Sensitivity and specificity. So there were two things that it talked about. Oh wow, I just want to confirm. Right. So specificity, true positives. Okay. I'm gonna look at the formula. Maybe it does say over here. Um, Here, there we go. Let's look at this. True positives. There we go. So true positive is the, okay, there we go. Here we go. Okay. So it's a true positive, not, I was going to say total positive, but that's good that I made sure that I was right. So again, sensitivity is basically the true positives, so the number of cases that are correctly identified, over the true positives plus the false negatives. And the false negative is basically the cases that were incorrectly identified as healthy, right? And then for specificity, like as long as you know the what these mean, the TP, FP, TN, and FN, it shouldn't be that hard to understand how to calculate the specificity and the sensitivity, as long as you know the formula, like especially within code, not too big of a problem. And then they talked about how figure 3 showed all of this stuff. We can look into figure 3 as well, which is on page 7. There we go. So this is what it's talking about: the accuracy, the specificity, and the sensitivity. So the performance of the glioma detection task, it achieved an accuracy of 86.3%, and then a sensitivity of 89.4%. It's basically all looking at the percentages, but and they're also explaining why it might have been like that. But again, what I really care about, even though the accuracy might be good, is like, how did they even come up with this novel approach? what was their thinking behind it, and what sort of techniques they use. The HOG, they use support vector machines. They basically just changed the entire status quo of how to use the HOG, and then you can see like they got pretty good results as well. Page 8, I would say, is a very, very good page to read if you want to summarize the solution. So again, we're calculating the HOG feature on every single local brain region, and that's like the cell in the algorithm. And instead of directly concatenating all of this, we're into one feature vector. We're actually first finding the high level overview of this, like, and getting more insight from that with machine learning methods. And then from there, we're applying the fuzzy clustering method. That's basically like the machine learning method that they're trying to find to see like the possibility of it being that certain cluster, that having that centroid there. So like, is it healthy, is it not healthy? Because yeah, that's why k is equal to 2, because it can either be malignant or it can be benign, or it can be diseased or it can be healthy. So that like thing in the middle, and then using a support vector machine to like kind of separate that data to see like, okay, what do you think now? Supposed to be uh is it supposed to be disease, supposed to be healthy, is it supposed to be malignant, or is it supposed to be benign? So obviously like that's really help summarize the content a bit. And then from there, after they use the fuzzy clustering method on the features, they're what are they doing? They're concatenating, yeah, they're concatenating all of this clustered stuff to actually look at the pattern for the disease brain regions for the whole MRI images. So like, now that you have these slices, now how are you going to put all that information to actually see? Well, when you're like cross-checking to see, okay, well, this slice says that it's like over here it's benign, here it says malignant, like it's easier to tell with the boundaries, because now you're like looking at the entire image as a whole. um so yeah, it's a very amazing summary, I would say, of all of this. And then along with that, I mean, there wasn't much else talked about in this research paper. It did talk about like how future applications could tie into this as well, because they said that they've used this analysis approach in things like Parkinson's disease, Alzheimer's disease, bipolar disease, and autism using MRI images. So obviously, like, it's making a huge impact. And this was before, but now with this novel classification network, there's also um, the potential for identification of tumor regions in neurological diseases, because obviously, like, tumors would play a big role in this too, not only the diagnosis of those diseases, because I mean, also for them, like it's really hard to go on certain things. Like for Alzheimer's, for instance, when I did my research, like looking at the beta amyloid plaques and the tau tangles, but within that, like that's very hard to tell. So using this method and like just looking at the tumors, things like that, getting more insight into neurological diseases, that's really going to help the biomedical imaging space. And that's why this was such a fun research paper for me to read, looking at the novel method of this two-phase classification neural network for the detection but also the grading of gliomas, because not only can we in the biomedical imaging space classify different types of tumors, but within those tumors, for every single tumor, you can gain so much insight into it. And I really found like that sense of looking at a micro level, like actually analyzing that specific tumor, there's still so much we can learn. And that's the potential of computer vision in biomedical imaging. Thank you for listening. See you next time.